Alright, so in this video I just wanted to summarize things before we get started. Summary. So if x changes from x to x plus delta x, right, then the change in y, delta y, is the actual change in y, right, which we can compute just by the difference of the f's. Then we have that dy is equal to f prime of x dx. These are the differentials. Those are the differentials. And we also had that L of x, which is f of a plus f prime of a times x minus a, is an approximation to f of x at x equals a. And if, these are the two approximations here, if delta, or I should say dx equals delta x, which it always is, then we approximate the actual change in y by dy. Good. All right. And so one other thing I wanted to mention, just a general side remark, a general note. We were talking about delta means change. Delta means change in whatever variable you're working with. So we know that delta y is the actual change in a quantity. The relative change to a quantity, let's say a, is given by the change in a divided by a. Now I'm using a because a could be x, it could be y, or it could be another variable v, for example. So for example, so again, this could be like delta x over x would be the relative change in x. Delta y over y is the relative change in y. Okay, and so on. And so this is just something that's used frequently without really defining it a lot of times. Okay, so let's go ahead and work through a few examples here. Let y be equal to the square root of x, and suppose x changes from x equals 1 to x equals 2. Compute the actual change in y and the differential dy, and then draw a sketch of these quantities. Alright, so first off, I guess we could go ahead and draw the sketch without really knowing what's going on. So here's the square root function, and then at x equals 1 we're drawing our tangent line. Maybe I'll draw the tangent line in red here. Good. And so x is running from 1 to 2, changing from 1 to 2, and so delta x equals 1, and that's equal to dx, right? Good. And so what is the actual change in y? The change in y is going to be the square root of 2, it looks like, right? Minus the square root of 1, which is the square root of 2 minus 1. So geometrically, whoops, that's not very straight. Okay, see if I can draw that straight. So that's the square root of 2 there, and this is the value 1 here. And so this value right here, I'll draw it over here. This is our actual change in y. Okay, and from the graph, by the way, you can see that dy is going to be a lot bigger, right? And so dy is going to be f prime of 1 times dx. Notice that f prime is being evaluated at the starting x, starting value of x. Okay, and so that's going to be, let's see, x to the 1/2 power, that's 1/2 x to the minus 1/2 power, evaluated at x equals 1. And then our dx is just 1, so that's going to be easy. Okay, so that's 1 over 2 square roots of 1. That's 1/2. Okay, and so dy is actually 1/2, and so geometrically, dy is this whole quantity here, right? This is dy, and that's, we just computed that to be 1/2. So let's see, I'm going to pause for a second and make a computation. Okay, and so the square root of 2 minus 1 is approximately 0.414. And so we see here that our change in y and our dy are very close together, right? And so often we will use dy to approximate delta y. Good. All right. Let's try another example. I guess a lot of my examples are have the square root function for some reason. So in the next one, I'm going to change the wording a little bit and see if we can figure out what to do. We're going to estimate the square root of 99.8 using a linear approximation or differential. Now, when we do this, we want to think that f of x is going to be the square root of x. Oops, sorry, not the square root of 10, the square root of x. And a 99.8 is very close to a nice number, and that is the square root of 100, right? So we're going to base our approximation at x equals 100. And so if we do that, what is our dx going to be, or our delta x? Did you say minus 0.2? If you did, you were right on. Good. So let's try both of these approximations. And so one is the linear approximation. Okay, so the linearization at 99.8, right, is going to be f of 100 minus f prime of 100 times x minus 100. By the way, you'll notice that that is our change in x, right? And so that is the square root of 100 minus f prime of 100. Where's f prime? I haven't computed it yet. F prime is equal to 1/2 x to the minus 1/2. I guess we've been doing that quite a bit, huh? 1 over 2 square roots of x. So it's going to be 1 over 2 times 10, right? And then this is going to be minus 0.2. Good. And so then we get square root of 100 is 10 minus, oh, that's 2/10 too. Okay. Minus and a minus is going to be plus, so I'm going to add. And so we get, oh, wait a minute. Oh, this is supposed to be a plus. Sorry about that. I thought something was fishy there. And so that's going to be minus, it turns out to be, that's 0.01. And so that's going to be 9.99. Good. Okay. How would I use differentials? Well, for differentials, I would take that my change in y is approximated by, so my delta y is approximately equal to dy, and that's equal to f prime of x times our dx, right? And I think we've already computed those, so that's going to be 1 over 2 times 10 times our dx is equal to our delta x, which is minus 0.2, right? And so the dy here is minus 0.01, and so that is, I'm going to approximate the change in y from that. And so my new y, right, is going to be my old y plus my dy. Okay, and my old y was going to be, it was at 10, right? And so, by the way, you'll notice that we're doing the same computation, right? Good. And so we get 9.99 either way. And just out of curiosity, if you do compute this on your calculator, the square root of 99.8 is approximately 9.899. So pretty close. All right. So try out some of the other problems in the book. We didn't talk about error, but you can think of the error as the change in y, right? The change in the computed value. And so I think the error exercises will be very similar to this. All right. Okay, I guess that's it for 3.10.